Yeah, as Alex said, my name is Richard Shepherd. I team lead and developer in the Cardiff Esri office, mostly working with C++, but have an interest in lots of languages, and I've been very interested in observing the growth of Rust over the last few years. Greatly helped by this meetup, even if I haven't got to use it in my day job. So Kira gave me this opportunity to try and get more actively involved with the current book. So I'm going to go at chapter 9, which nicely pulls together quite a lot of what I've managed to, I think, get the gist of over the last couple of months that everyone's been working through the chapters. So I'll try and re-explain it to everyone else. I'm happy to try and answer questions, but I can't guarantee that uh, I know I don't have deep knowledge about it. I just about have a mental model of what's going on and how to start experimenting with it, but happy to discuss. Anyway, this chapter is all about trying to put together some of the concepts to build some uh, blocking mechanisms that we can make use of in our threaded software, using the sort of lower level things we've been talking about recently, in particular the sort of low level operating system functions like wake and wait, which exist on various platforms in various forms. Apologies that I can't persuade Markdown to show me the whole table at once, so you get to watch me scrolling through the different versions that the OSs have for implementing the wait and wake instructions. These are nicely packaged up in the atomic weight crate to play with it. And you've then got access to wait, wake one, and wake all. So those low-level constructs are what we're going to be using to try and build our higher level objects out of today. In particular, wait takes a U32 value and compares, waits until that value is not equal to the value you give it. Yes, yeah. It blocks while it is equal to the current value. I always have to stop and think and make sure I'm getting the logic the right way around. It relies on you knowing a value you want it to stay blocked on, and it finishes waiting when that value has got a different value. The complementary instructions, wake one and wake all, allow the are used so that anything that is waiting can be informed that it's now worth having another look at that value. Wake one wakes one thread, and wake all tries to wake all the threads. Potentially, the wait can spontaneously or sporadically notice a change, even when it hasn't been strictly woken, or equally, you might find you're waking too many, even with a wake one, but we'll get to some of them, those problems in a bit. Okay, trying to build sort of the most straightforward structure, mutex, which I'm somewhat used to using, but mostly from C++. So at least I'm aware of how I commonly use them in code to take control of something, or to wait until I can have control of something before working with it. In this case, the mutex here is wrapped around the object we're interested in. The data is the T type. The mutex itself contains the extra information about whether whether we can have access to it if it's unlocked, or whether anyone else already has it locked, and we're going to have to wait on them. To be able to share this between different threads, which is when it's useful, we need to convince Rust to allow us to do so. We need to create the sync trait, or specify the sync trait for the mutex so it knows we're allowed to share it between threads, and we enable that for whenever we consider it safe to send the type T between them. Most of the work is done by the mutex guard type that's used to I guess, create an RAI structure when we want to take control of the mutex and have it dropped automatically when we've finished, with the data that's been protected by it. So the mutex guard itself is what we'll create in our code, and we'll then be able to dereference it for write access or read access. And those are the not very interesting bits. The interesting bits are how we control actually locking it when we're trying to take it. So to lock the mutex and give us a mutex guard, we want to set that state variable we included inside the mutex. We want to change it from being 0 to being 1. So we want to do everything. The state itself is atomic, which means we have to use atomic operations on it to make sure that nothing else can see anything while we're in the process of examining and changing anything. So we have a small range of operations that we can use, such as swap. In this case, we're trying to swap the value 1 into the state to lock it for ourselves. And if the swap itself will return the value it already had. So in this case, it's returning a 1. So, if it returns a 1, that means it was already locked by someone else. So we can't take over the lock for it, at which point we now want to wait and go to sleep. Effectively, we block at this point in the code, and until we see that state become something other than 1. Yes, because it's currently 1, so we want to wait until it's not 1. Right, at which point we go back around the loop again and try and put our lock into it. At which point, if we were the one that was able to swap the 1 in, the previous value would have been 0, and we will break out of the while loop and finally be able to return the mutex guard that the calling code keeps has in its scope while they get on and do the actual work they want to do with the data, using the deref to actually access the contents. And then when their scope finishes and they want to drop the mutex guard, they then put 0 back into it. They don't need to worry about what current value it's got. It'll either be 0, which it shouldn't be because we've got the lock on it, or it would be 1, in which case we want to unlock it, so we just set it back to 0. We also then want to wake up anybody else who might be listening on it, so that they get a chance, because that's the trigger for anyone who's waiting to really look at their values. If we never sent the wake, then they could be waiting indefinitely. You could call wake all, so that if you've got multiple mutex guards all waiting for it, they'd all wake up and try and grab it, but only the first one would successfully get it. The others would all have to go back to sleep again anyway, so you're no better off than if you just called wake 1. I was trying to think of a scenario where wake all would be useful. Something like, I don't know, some of the threads maybe work a lot faster than some of the others, and you're hoping by doing a wake all that the faster processors will get a chance, and whereas a wake 1 might accidentally keep waking up the slow one or something. I couldn't really come up with a scenario where wake all would help you a lot. Okay, you can still get problems, or not necessarily problems. It may not work quite the way you expect. You may have a mutex guard that is waiting on being woken up, and just as we store the 0 in the state, a third thread tries to create a mutex guard, spots the 0, immediately uses it and locks it. The wake 1 woke up the second thread, but by the time it starts looking, it's too late. Another mutex has come in and grabbed it. Noticeably, this code works if you take out the wait and the wake. It would just spin on the loop until it could grab the value. So it would be back to being a spin lock, which I think we've looked at in previous chapters. But it definitely helps me sort of with my mental model of what's going on to try and verify that the logic is correct if I can picture how it would all work without the weight and the wake. And if it seems to be entirely dependent on them being there, then I'm suspicious of my logic. Okay, the slow parts of our mutex are the actual wait and wake calls, because they are calls down into the kernel to call one of those operating system instructions. At the moment, we can't do much about the wait. We're waiting whenever we know it is already locked, but maybe we can do something about the drop. So if, for instance, we modify the state variable we had so it wasn't just unlocked or locked, but also kept track of whether anybody was listening, then we might have a better idea on whether it's worth calling wake, if that's going to take time.
I'm sorry, Richard.
Sorry, Alex.
That's all right. Just before we carry on, we have had a question in the chat.
Yeah.
Apologies, Asherman. I don't know when you asked this a few minutes ago, I think, but when many are waiting on a convar, I was just wondering at what point was that in relation to? Sorry.
That could have been in relation to when I was asking about when wake all would be useful.
Yes.
Which would make some sense. We will get to conditional variables in a minute. That's the sort of middle third. Although it doesn't, I don't think, touch on that particular use for them. But no, that's quite possible. Thank you. I'll have a think about that. Okay, getting back to any other questions in there at the moment? No, there aren't. And yeah, thanks for RAII. I apologize for the horrific name. Back on this lock-in. Okay, so if we were locking, instead of what we used to do where we compared against 1, and now we are looking to see if we are not equal to 2. Okay, yes, that's right. We're trying to swap it to the value 2, which would indicate, mouse is on the wrong screen, that they now are listeners. So we're trying to indicate that we are listening. If the value is not 0, so somebody else is already listening, or somebody else has already got it locked, then we're going to wait until it's no longer equal to 2, which it could have been currently. It might also have been currently have the value 1, in which case it would wake up, or it would wake up as soon as it goes to 1, which would mean someone else has got it locked, and we would try to swap the value 2 in to specify that we're now listening as well. But eventually it'll hopefully get down to 0 so that nobody else is locking it, at which point we can jump out and release the mutex to actually be used again. The drop side of it is now where we now have the extra logic that if it was previously being listened to, then we do wake up one of the other listeners, whereas previously we were always waking up. Yes, so we waked in all conditions every time we were dropping it, whereas now we only call the wake if we know that somebody else is listening. So it should save us that call. We can also look at another case where we are trying to avoid the wait, or at least potentially do something that's faster than a wait in common cases. Namely, we're going to deliberately use a spin lock, which is not going to use the syscalls, and gives us a good chance on things that are only held very briefly that we will pause, wait briefly, and see if we can load the state and get access to it and lock it ourselves. Sorry, checking that it is. Yes, while it is locked, then we keep spinning. It's only and then while it isn't, we come out. We then do one additional change to change it from unlocked to locked. Check, make sure that we're able to do that. If we are, then we can come out of our lock contended function and return the mutex guard as we want. If we weren't able to lock it ourselves, then we again set it to the state 2 to indicate that we're listening, and go back to the same state we were in before where we're waiting on it, using the syscall. So we have an initial chance to hopefully do something faster than a wait. And in the chapter, the author actually did do some comparisons to see how much difference it would make. I'll come back to those in a sec. So certainly, when he used just the 2 threads waiting, one writing, one reading, it made a big difference. Having the awareness of whether there was a listener or not. It dropped from, by 10-fold or 20-fold or 30-fold. Although not on the Mac, didn't make any difference whatsoever there. Although given the size that they were getting without the optimization, it sort of gives you a clue that Mac is basically already doing the same optimization in its lower level functions. A separate performance test where the author looked at using the spin lock. Less drastic effects. On an older processor, it made a small difference. So I guess that's 20%-ish. And in fact, on a newer processor, it made things worse. So whether that's the syscall being more efficient than expected compared to the spin lock, just having the lower complexity in the code. But it's certainly a reminder that certainly if you're going to make the code more complicated, be certain it's actually going to make a difference that's going to be helpful. Just going back briefly to some of the things that's mentioned in the code, it used the stud hint spin lock, which I hadn't seen before. This line in here, which is a hint to the compiler what you're working on, and you are able to jump to documentation on it. Why is that coming up anywhere? It is. A horrible feeling that's just what was it able to optimize? That's right. It was because it knows what you're trying to do. It potentially can invoke or would take the liberty of invoking other instructions to try and reduce what that process is doing. Phew, that came back. And there's suggestions in the book on other directives you could also look at. Things like hash cold to indicate that, for instance, the lock contended branch is not something that is expected to be hit very often. A lot of the time, if you expect this compare to work I guess, so the branch prediction to mostly not error, then you can mark the lock contended or the function itself as the unlikely to be used branch. So the compiler can take that into account when it's generating its code. And what was the other one? Inline. Inline, from my rough reading, seems to work the same in Rust as it used to do in C++, which to my mind nowadays means use it at your peril. Relying on putting the code in place doesn't seem to be a particularly good guarantee that it's going to run any faster. You certainly need to profile it and be certain it's worth it. I think nowadays in C++, it's primarily used just to indicate that there should only be one instance of this rather than thinking in terms of it putting the code in place at the point of call. But I don't know enough about the Rust one. But certainly in the book, it suggested it should work for very small pieces of code and should be an improvement. But given how easy it is for even small pieces of code to actually be calling other things that are doing quite a lot of work, I'd be I'd be suspect before using inline. I'd certainly profile it. And I guess come back to profiling it again in future versions is sort of thing that changes with versions of compilers. Covered that. Condition variables. I got to admit, I found this the hardest part of the chapter was getting my head around condition variables. I had to reread it and go back to the earlier part of the book where it sort of went over, summarized them more briefly. I guess they're not a mechanism I've used before, so it took me quite a while to sort of get how they linked in with what we were trying to do with the mutexes and the threads. But I think I've got it fairly clear. Okay, the example they start off using in the chapter is one that we encountered earlier, where you've got two threads, one reading from a vector if it contains elements, and one writing elements to the end of a vector. So these the manual code without using any condition variables, just got a mutex to protect the queue that we're unwrapping. So we're looping indefinitely to read items off this queue. Each time round the loop, we take a lock on the queue. We get our mutex. We try and pop something off the end of it or off the front of it. If we're successful, then we drop the mutex. So we've now released it so that the other thread can try and push things onto it. As soon as we've done that, we get on doing our processing with the item. In this case, just dump it out to the console or to the debug stream and continue looping round. The bit that I had to keep reminding myself about is how long the queue itself is blocked for. Not so much in this example where it's fairly clear we're taking the lock at this point and then it gets dropped at the end of the scope, but more when we got onto the next bits of code when I was trying to keep it clear in my head when it was locked. Once we finished reading, where's the brackets going? So that loop lines up with that. Got that. So I'm just trying to work out the line up. Yes, so the sleep is inside the same iteration inside the single iteration of the loop. So we at most are outputting one item at a time before we sleep. Meanwhile, the other thread's trying to push them on. So how could we do this without just waiting an arbitrary amount of time? We're going to use our condition variable to try and notify the waiting thread that it's now worth checking the vector to see if it's got an extra value. That way we're avoiding locking the vector if it's not worthwhile doing so yet. So we're creating a new structure, our convar conditional variable. And the way we'd like to be able to use it, looking back through my notes, couldn't actually find this in the book. So I have a feeling this was just me doing what I thought, trying to be clear in my head how the previous code would change if we had the convar. Either that or I just can't find the page that this bit came from. So we're still initially blocking the queue while we try and take a value from it. We are looping to get an item out of the front of it. If we can, then that's fine. We come out of that loop and do the same as before. If we can't get anything off it, then we are now waiting on the condition variable, not empty, being triggered so that we can then proceed back round on our loop to take another look at it. I'm just trying to remember. Oh, yes. So yeah, it took me quite a while to try and get the hang of this because we have taken the lock here. So it took me a while to work out how we weren't keeping this lock on the queue for a very long time. But crucially, we only keep the lock until we, if you like, enter the wait. During the wait, the queue is unlocked, allowing other threads to get at it. And at the end of the wait, by the time we return it, we've now locked it again. So the idea is that all the code within this can treat queue as locked. It's only unlocked while we're waiting. And then finally, on the iteration, we again drop it. So we're back to a drop state of releasing the queue, do our work on the item. If this wasn't just debug, it could be quite a lengthy bit of work we're doing on it before we iterate round again. In the writing phase, doing for time. Okay. In the writing phase, we every time we push an item on, then we're sending a notification that is what the waiting is waiting on. Okay, the interesting bit is how wait and notify are interested. And notifies, all we're using for our convar is a simple count. It's not a Boolean locked or unlocked. It's an incrementing counter. Because what we're going to look for in the wait is just any change to the current value within the state, rather than it being a specific value. So our notifies, all they have to do is make a change. In this case, just adding 1 to it. The wait part, we're going to load what the current value is. This is the part where I was talking about, where at the beginning of the wait we drop the guard on the data or on the mutex so that other accessors can work with the mutex while we're waiting, and then we wait until the counter that we're tracking inside the convar changes to anything other than our current value. At which point we will relock the mutex and return with it, and our code will be able to continue. It does point out in the book that there is a danger that while if you were really unlucky, in between you unlocking the mutex and getting around to checking that your counter could have spun all the way around through all the unsigned ints back to the value you started with, then you might not notice. But it seemed to feel that there wasn't a huge risk of that, or something else has gone badly wrong. As I said, it took me a while to get the hang that the convar is almost more. I ended up seeing it more as a sort of broadcast mechanism, letting the waiters know that it is worth looking at again. It took me quite a while to sort of understand the relationship between the two things, and also that the logic of when things were locked and weren't took a while, because I was used to seeing an object being held while you're keeping it all locked, and the code in there taking place during that phase, whereas this was the opposite. You were unlocking it while doing all the waiting. It did, after a while, start to look analogous to some of the stuff I'd read or watched talks on coroutines, where you were sort of naturally pausing at the wait until something happened and then continuing with the next part of your code, and that seemed to line up with other async concepts. Finally, the bits in italics, by the way, are my ramblings rather than anything the author has far more knowledgeably said. But the author did say that testing is important for these kind of mechanisms, to make sure that they are actually working, because you could easily get the logic wrong, still get the right results on small numbers of threads, but unless you're checking, you won't know whether you've accidentally just been spinning. Okay, I'm aware, plowing on with time. Okay, some of the optimizations you could try and do with a conditional variable. Again, similar to what we did with the mutex, trying to avoid any waits or wakes. In this case, the wait can't do a great deal. We're already well, we know we're having to wait by the time we're calling this. Um, so we're just gonna have to make live with it. Oh, where's it gone? Whereas in the wake case, we can try and see if, again, anybody else is waiting on it. So if we track the number of waiters on our conditional variable, and then in our notify instructions, if there are any waiters, only then do we bother calling the wake, or even changing the counter itself. And similarly with the notify all, it's exactly the same logic, but we just wake all the possible waiters rather than just the one. The wait method is a bit more interesting in that they now have to register that they're starting to wait. So they increment the number of waiters, and that should almost certainly be sub, not sum. Subtract it by one to reduce it down so that the so that we've got it bracketed when we've stopped waiting on it, so that any of the notifiers can see when all the waiters have disappeared. Other than that, it's the same. Okay, probably the most technically complicated part of this chapter is the use it makes of the memory ordering, whether things are relaxed or having to use require, release, and acquire. I am not certain enough about them and probably don't have enough time to cover that aspect in detail. During this talk, I did spend quite a bit of time trying to think through and understand when they were needed, but didn't get to a solid enough point that I could explain it in detail. They, I get the basic idea. You've got the happens before relationships in here. We're using relaxed throughout. When do we start using it? If we haven't got an example, I'm definitely not going to try. Okay, so for this, the author was able to analyze it and convince himself, if not me entirely, that it was safe with just relaxed loading, that it would definitely happen in the right order. Using them accurately seems to still rely a lot on our reasoning ability, which is it's not like the Rust isn't going to save you from using the wrong one or getting them in the wrong order. You have to use your reasoning, but having them explicitly in there every single time you use one of these operations does at least document your expectations about how it is going to work, and it's encouraged to document alongside why this is sufficient order and protection. But it's something I'm going to need to spend more time on to, if I was going to work with this and try and build my own memory management tools. Just try and move on with some of the other optimizations for this. What were we doing? What was wrong with that? Counter changed. So in this, yeah, this was the bit of code we added, that if there are waiters, if there are any waiters, then we try and do the wake. But similar to the example I mentioned earlier, you could have another waiter join in, spot that counter has already changed, because of the fetch add, before the wake one got called, waking up another waiter. So those are examples of when you might have um, more threads waking up than you were hoping. You've called wake one, but you may actually have several um, waiters trying to make use of it. And according to the author's experience, this can actually happen more often than you expect, because the whole process of having something like a mutex lock-in tends to mean that you're going to have one or more threads effectively being synchronized by at that point, by that value. They're all going to be potentially several threads all waiting on it, and as soon as one gets notified, you can get into a cycle where they're all being created at more or less the same time. So uh, the sequence of locking and waiting can end up becoming very closely synchronized. They're not completely independent and arbitrary. So you actually get these um, spurious wake ups more often than you'd expect. There are techniques for trying to get around that if it's a problem in your system, but they all involve adding more and more complexity to the code, and may have other more subtle effects. Fairly well known example appears to be in the GNU library, that they had this problem for a long time, and it was a well-known problem until they ended up by using an entirely different algorithm and having to add quite a lot of heavyweight machinery to have groups of waiters so that they could distinguish them. More straightforward problem is the brilliantly named Thundering Herd problem, which is more specific to notify all, where you wake everything up, they all try and grab the same mutex, only one of them can, so most of them go back to sleep again, or waiting until the count changes again, and then all the remaining ones all wake up and only one of them can get it. And it's there's the suggestion that anytime you're using notify all, maybe the problem is just the concept of notify all rather than anything we can specifically do about it. It can be worked around a bit if the operating supports a mechanism called requeuing, which the gist of it, from what I could gather, is that it is basically lighter weight to requeue something than to wake it and have it go back to sleep again. Again, requires more complexity in your code, and in particular, it needs to be much clearer on which mutex the variable is referring to, so that you can requeue it. Finally, the reader-writer lock, which I found much simpler concept than conditional variables, possibly because it's actually very reminiscent of Rust's own ways of managing references to things, where you can have lots of readers or only one writer. In this, we want to enable that across threads. So again, we're going to build our lock around our data item. Now, whereas before we only needed our mutex to support send, we now want the data itself to be readable on multiple threads at the same time. So we require it to have the sync ability on the data type itself. And because for a read-write lock, we now want two different ways of using it. We need two different functions. Rather than just having a single lock function, we've now got a read function that will lock it for us to read, or but allow other read locks to be taken, or write, which means we've got exclusive lock on it. Each of which will give us a guard object of the relevant type. Anything else in there interesting? I guess the crucial bit is the state that it uses to manage what state it's currently in. We need two different dereference methods, one for the write method and one for the read method. So the read one is allowed the non-mutable dereferencing. The write one allows us, or the write guard allows us to do either mutable or non-mutable referencing of it. We're not forced to change it. Then the more interesting part is the read method, where we're actually trying to produce a read guard. So we want to allow lots of these, but only if there are other readers and no writers. So the way we're indicating this, and I'm slightly surprised it didn't come up earlier. Oh, yes, it did. Crucially, the state we're storing is the number of readers, or it's using the max value to indicate that we've got a writer. So in here, the code when we're trying to take a read guard, first of all, check whether we've only got other readers. So the number is less than the magic value we're using, the max value to indicate the writer. If there are only readers, then we attempt to add one more reader, namely ourselves. So if that works, why wouldn't it work? It wouldn't work if the value by the time we were trying to do our compare had already changed from what we were expecting it to be, because it might have already been decremented and taken over by a writer. So the compare exchange week will check that the value will atomically check that the value is what we expect it to be, exchange it with the value we want it to have, and return us information on whether that was successful or not. If it was successful, great, we've taken a read guard and we can return that. If it wasn't, it's changed to something else, and we are then we're going to end up looping back round. Before we do that, we just check if it is a writer. Then we know what we're waiting on. We're waiting on the state being anything other than the writer indicator value. So we can just wait on that. If it wasn't, if we had an error just because the number had changed because another reader had taken another guard in the meantime, then we won't go into this if block. We'll loop back round. We've got that new S and we'll try again to see, okay, well, let's increment it one more. So I guess if you've got lots of readers all trying to join at once, they can keep getting in each other's way. We've also got this slight extra condition here to make sure that we don't accidentally get so many readers that they suddenly look like a writer and jam the whole thing up. In this case, all it's doing is just panicking if that happens. Whether there be other more useful things you could do in the code, presumably you could arrange something so if you got that high, your reader would also need to wait until at least one of the readers disappeared before they could take a lock on it. The write lock is much simpler because all we've got to do is worry about, we can only do it, we're going to use the same compare exchange idea. If there's currently nobody else reading or writing it, then we set it to our writer value. And if we have a problem doing that, i.e. if there is already some readers, then we have to wait until the number of readers changes, at which point we will try and see can we change it from 0 to the max value for writing. If we're successful, so we don't get an error out of it, then we immediately exit the loop and can just return the write guard and get on with the work that we were trying to protect. Okay, the actual drop-in part is where we need to keep everything in sync. So if we've got a reader that's finished, then it is now able to subtract one from the state, which subtract one of the readers, and also wake up anyone else that's waiting on it, which would typically be a writer. The writer will currently be in, if you've got a right guard, that means it's jumped up to max. So the only thing you need to do is drop it back to 0 so that any readers or another writer can have a go at picking it up. At this point, whereas with the writer, that's the point. Why did it want to use wake one? I was going to say with wake one, you know there's only one writer, but that's not true. You might have several people waiting to write. Just wondering why you would definitely use wake all in that case. Hmm. Right. Can't ponder it now. But moving on with the optimizations for it. You could have lots of readers, uh, and the writer's weight. If you notice, um, on the right, when you're trying to get a right guard, it's waiting until the current number changes to anything else. So you might have 1,000 readers. This changes to 999, at which point you come out of the wait and you go around and you try and capture it again. You still can't capture it because there's 999, so you go to waiting again, and all those waits are expensive. So can we do better? The first suggestion is rather than waiting on any change to readers, wait until it goes from 1 to 0 readers. Basically, you wait on the last reader, which is actually more work for the readers than it is for the writer. So on the writer side, he check. What it does mean is that we need to distinguish between um, writers and or we need to distinguish between the number of readers that we already had and something else to indicate that we want a writer to now wake up. Because yeah, it might seem at first it seemed natural to me. Well, why couldn't the writer just wait on the state becoming 0? It's because wait has to wait until the value is different from your current value, not until it's equal to your preferred value. So adding a second atomic variable that you wait on instead is the way to change what you're waiting on. So in the case of the right guard, it's now going to check whether it should be woken up. If it so that's what's coming in the right awake counter, whether to wake up or not. It also checks the state to see if it is 0 or not. So remember, 0 is when it's not locked by anyone, writers or readers. If it is 0, then it jumps straight out and is able to just take the guard itself. If it isn't 0, then it goes to sleep. It waits until there's any change to the right awake counter. So the separate flag, if you like, or counter that's going to tell it that it's worth a writer waking up. So now the work for the read guard is, instead of previously where when you dropped it would always change the state, it still always changes the state, but now looks at the previous value. And if it was at 1 before it did the subtraction, then it knows, right, this is the last reader, at which point it can send its signal or update the counter for the writer. So this is hopefully far less often than previously, when it was effectively waking the writer or the potential writer every time there was any change in readers. So we've got the wake one on the right side. It also needs to, yes, the writer similarly might need to wake up another writer that's been waiting on it, um, as well as waking up any readers that were waiting on the right. So notice that it's waking the two different variables for different purposes. Another problem that could stop lots of readers getting, meaning a writer doesn't even get a chance. That particularly if I guess writer readers are I can't remember the scenario that they suggested was different to what would stop causing the previous problem where that's right. Previously, we were worried about the writer waiting a lot, whereas now we're worried that the writers may just not be getting their chance to ever add anything new to it because different readers keep jumping in and taking all the slots. So the suggestion is here that once a writer is waiting, because the readers presumably want to read what's being written, and if the writer's never getting a chance, there's nothing new to read. So if to block readers if there's a writer waiting. So you can't create, you don't stop existing readers, but you stop any new readers. To do this, rather than yet another flag or counter, the author suggests a technique of making more use of the existing state. So we're now going to increment it by 2 every time a reader takes it, and add a 1 on if there's a writer waiting, not locking. So that way we gain more information. Effectively, we're using 1 bit of the 32 bits to indicate that there's a writer waiting. It does mean we can't have quite so many readers now. Putting the 2 bits of information together allows us to manage it all within 1 atomic variable, and only needs to, I guess, do operations on 1 at a time. You know, if we separate it into 2 different bits of information, you've then got to worry about those being synchronized or getting, having atomic decisions being made on the 2 pieces of information. We want to use the 2 pieces of information at once. So the easiest way is if you can actually keep them together in 1 atomic variable. So in this case, the read is now changes slightly to check whether num values are even or not. So even in this case would mean we haven't had a 1 added on, so we haven't got any writers, so we can try and have another reader. So they try and increment it unless the value's changed by the time we get to try and do this. But if we're successful, then it's the same as before for readers. If it is odd, that means there's a writer already waiting, and this is the condition we were looking for. If there's a writer waiting, then we want readers to wait until there are no writers waiting. So we go back to sleep until the number has changed, whether it's gone down by 1 because there's no longer a writer waiting, or if it's gone down by 2, then we'll similarly get woken up anytime there's a change. Even more detailed is the code for the right guard. I won't go through all of this in detail, but it is pretty much as you'd expect. If you've got nobody waiting, no writers waiting, or only 1, I did convince myself that was correct. Then we attempt to take control of it and lock it, and return the right guard. If it's currently, there are only readers currently, but we haven't been able to take the right lock, then this is when we increment it to specify in the state that there is now a writer, namely us waiting, at which point we go back to sleep to wait for it, to wait for our indicator, the wait counter to tell us that it's now worth having a look because all the writers, all the readers have disappeared. And how does it indicate that there's no writer no longer waiting? I can't remember. Was that on the next iteration? Right. I know I'm about out of time, so I won't try and work it out now. Similar optimizations to try and reduce how often you're calling the wake. If we know, yeah, so don't try waking the writer, run doing it all the time, only do it if we definitely know there is one. We don't have any information when we have got a write lock. So we just have to, we don't know if there are any readers or not, so we just have to signal everyone still. And that is it. So it was I found it a really good chapter. Doing it was as much explaining the mechanisms that would be true if it were relevant if it was Rust or any other language. Similar language where you'd need similar constructs, but then using Rust to actually implement relatively safe and simple versions of them. Certainly still hard work to get them right. It was interesting in more or less very similar optimizations being used in each case. It was mostly concentrating on trying to limit the waits and wakes. But the logic is understandable, particularly if you mentally separate out the wait and the wakes or the notifications from the rest of the logic. You should be it should be correct even without them. It's just not as optimal, so you can focus on it being one part being the optimization technique interspersed with the logic that should work regardless. Testing already mentioned earlier, and yeah, all the optimizations that we saw all added more and more bits into it. Some of it's, I mean, the most simple version of these mechanisms, it was pretty easy to get a pretty bulletproof first off. As soon as you started adding these optimizations in, there started being a lot more complications about making sure you've thought about everything and worrying more about the memory order correctness. So certainly add each layer of optimization as you're definitely certain you need it. That's it. Hope it made some sense to you guys and helped a bit. Happy to chat. Not sure I can necessarily answer too many in-depth questions, but I'll stop talking.
Thanks very much, Richard. There's quite a lot of content there. So I'm amazed you actually got it into roughly into the hour. It's hard going, I bet. Yeah. So does anybody have any questions for Richard? I'll just check the chat. We haven't got any more in the chat. Some thank yous though.
There's a number of things that I want to go back and look at some more, like why I'm not quite sure now why it ended up with one branch using the wake one using the wake all. So I'll have another look at that, as well as thinking a bit more about it. What I really want to spend more time on though is the memory ordering correctness and make sure I understand them better. And I think I need to build some examples, deliberately use the wrong, use too lax an ordering, and then try and get it to go wrong so I can convince myself when I need to use the release and acquire. Because I can sort of see the idea with the release and acquire that you're guaranteeing that everything that happened before the release definitely happens before any other thread sees anything happen after the acquire. But then when you put it in a loop, so you're getting a release acquire, then I start to get less certain that things are definitely going to happen in the right order. But so I need to rewatch because I think that was covered more in an earlier chapter. So maybe I had to rewatch that talk and try and build some examples. I should also mention that you almost certainly don't need to build your own condition variables on mutexes because they are all there in crates being carefully built by people who spent a lot longer on them.
I wonder how much of this chapter you can apply that sentiment to. Um, if there's no immediate questions, I do just have a few details about some upcoming meetups to go through. And I'm not going to cut you off if anyone thinks of a question. Just we'll cover it in a minute. I'll just take over just for a sec, Richard.
Go for it, Alex.
Can you see that? Okay.
Yep.
Brill. Yeah. So just a reminder that on the 29th of November, which is in 2 weeks' time, Tim, I think it's Tim anyway, will be taking us through the final chapter of the Locks and Tonics books, Ideas and Inspiration. Then that same week, on the Friday, the 1st of December, we'll be kicking off the Dragons Christmas Game Jam. So there's full details in Discord at the moment. But the way it's going to work is that we'll all hop on just like this at the same time, 6:30, and I'll just run through the rules and I'll announce the theme for the jam, and then we'll open up some new chats and spaces in the Discord so people can throw ideas around, form teams, and get into the collaborative spirit. And then you can work in your own pace over the next week. And so the following Sunday, so the 10th of December, we'll get we'll get together again in Zoom, just like this. And each game, each team, each entry will just be asked to give a very small lightning talk. I mean, really small. We'll probably cap them at 5 minutes each. I imagine we'll have quite a few entries, and just to show off what you've done, what you've made, what you've learned. We'll do a little bit of not serious voting at the end, just to pick a few winners across different categories. So yeah, please join us for those. That will see us through to the new year, and we'll have more details to share about what's coming up from January after Christmas.